This topic is about the creep and the fatigue properties of a modified HR3C. And this work is also with one of my colleagues, Lu Yang. I will introduce it from the introduction, experiments, test results, and conclusions. Austenitic stainless steel HR3C has been developed for high temperature applications in the advanced ultra supercritical power plants. So in service, creep strength is an important factor, and the components generally enable low cycle fatigue, which is also an important factor. This implies that the creep fatigue interaction is also of importance. So in this work, creep low cycle fatigue and creep fatigue properties of modified HR3C are investigated. Now it's about the experiments. First about the equipment. For the low cycle fatigue and the creep fatigue tests, it were performed using the instrument system, and the test temperature was controlled within 1 degree. Here is the low cycle fatigue machine in our laboratory. And this is the chemical composition of the modified HR3C. So for the modified steels, the chromium, niobium, and the nitrogen content have been increased, and the tungsten and the copper have been added. And it needs to be stressed that for the modified version, the composition is still within the minimum and maximum values of the ASTM standard. The specimen were extracted from tubes like this. And for creep, we use the cylindrical specimen. For low cycle fatigue and creep fatigue, the rectangular specimen were used. For the test conditions, the creep it was conducted at 2 temperatures, 650 and 750, with different stress levels. For low cycle fatigue, first it's the creep fatigue. It was conducted with the hold time of 5 minutes at the maximum load stress. And for both the low cycle fatigue and the creep fatigue, the test temperature was 700 degrees, and the strain rate was 10 power minus 3. The total strain range was 0.4 to 1.5%. During the test, the failure was considered as a 60% drop of the maximum load. And then here I will show the test results. First, it's about the creep rupture strength. This figure shows the creep rupture stress as a function of the creep time. This is the experimental creep data at 650 and 750. The lines here is the results obtained with the master equation from HR3C. So compared with the master equation, so the current result is lower at 750 and much lower at 650. And also during the creep test, the low ductility has been observed, where the reduction in area is about 4 to 19%. And also the low ductility, it also affects the creep fatigue properties of the material. We will show it later. Here for the lines, it's the master equation. It's an equation developed by the HR3C, European Creep Collaborative Committee. And with given stress and temperature, the creep rupture time can be estimated. And this equation is for HR3C. And here beta 0 to 5 are constant parameters. For creep fatigue, during the whole time of the creep fatigue test, the material is exposed to pure creep, so the total hold time can be considered as the total creep time during the test. Therefore, it's naturally to compare the total hold time to the creep time. And here, this figure, we compare the total hold time with the creep time. And the black one here is the total hold time of the creep fatigue test at 700 degrees. And this is the creep time at 650, and this is at 750. So compared with these two temperatures, and the current results here, it lies in the two temperatures as it should. And this is the results about the cyclic response of the modified HR3C at 700 degrees and both the low cycle fatigue and the creep fatigue conditions. This is about the total spin range, so as a function of the number of cycles to failure. And here it's the plastic spin range versus the number of cycles to failure. The black one in these two figures, it's the low cycle fatigue test results. And the red one is the creep fatigue test results with hold time of 300 seconds. So in both figures, the number of cycles to failure, it decreases with increasing total spin range and the plastic spin range, and they are in agreement with the Kofi-Munson equation, which is the dashed line in the figures. And if we compare the creep fatigue with the low cycle fatigue at a given total or plastic spin range, there is about 1 to 2 order of magnitude decreases in the number of cycles to failure. And this is the stress amplitude versus the plastic spin range. So for creep fatigue results here, it shows the lower stress amplitude. We also studied the metallographic. And here it's the SEM images of the creep samples at 650 and 300 MPa. So the cavities were observed along grain boundaries, and also it shows intergranular fracture. This figures it's the fracture surface of the material at 700 degrees, and this is at low cycle fatigue and the creep fatigue. So in both conditions, the intergranular fracture were observed, as you can see from here. For the microstructures, so in the material, the primary Z-phase particles were observed unevenly distributed, and mainly they are not small enough, which may result in the low ductility. And also cavities are formed along grain boundaries. Besides, the oxides and inclusions were also observed. The test results of the low cycle fatigue test results we compared with the Sanicro-25. Sanicro-25 is a new austenitic spin steel developed by Sandvik. It's a very competing material that can be used for high temperature advanced ultra supercritical power plants. It has good high temperature creep and fatigue properties. And this figure shows the comparison of the low cycle fatigue properties of the modified HR3C and the Sanicro-25 at 700 degrees. So this is about the plastic spin range as a function of the number of cycles to failure. So both materials present a similar behavior, whereas the number of cycles to failure it decreases with increasing plastic spin range. And then the number of cycles to failure for the HR3C here it's about 1 to 2 times longer than Cr25 at a given plastic strain rate. And this figure shows the stress amplitude as a function of the plastic strain rate. So a similar cyclic stress strain response was observed for the two materials. And for given plastic strain rates, the HR3C variant shows a slightly lower stress amplitude. Some conclusions. First, the creep low cycle fatigue and the creep fatigue experiments were performed at 650 to 750 for modified HR3C spew. And the creep effects have a significant influence on the fatigue life, which reduces the number of cycles to failure by 1 to 2 orders of magnitude. And the fractography shows that the main failure mode was intergranular. The number of cycles to failure for HR3C variant was 1 to 2 times higher than for Cr25, and also similar cyclic stress strain response was observed for the two materials. Thank you for your attention.